All right, this is Mr. Conaway. Welcome to the Chapter 7 of the, hold on, there we go, Spring Exam Review. We're going to start on Chapter 7 here. I don't know how many I'm going to get to a recording. I like to keep it around 10 minutes so that I can upload them to YouTube easier. So probably Chapter 7 and 8, I would think, and then we'll go from there. Starting with Chapter 7a. Point M has the coordinates negative 3 comma 2. What is M prime if M is reflected over the following? A is the x-axis. So if we draw out negative 3 would be about here. 2 would be about there. So that's the point negative 3, 2. If I reflect it, so this point right here, if I reflect it over the x-axis, this is the x-axis. So the reflection should be down here. And what we remember is that the distances here should stay the same. So when we reflect across the x-axis, the distance from the x-axis is going to be the same as the distance on the other side. So since this was up 2, this is going to be down 2, which means that this point over here is at negative 3, negative 2. So the answer is negative 3, negative 2. Okay, 7b. How about if I do it over the y-axis? So, once again, if I do negative 3 comma 2, somewhere in there, it's going to be reflected across the y-axis, so that means that this distance is going to equal this distance, and we'll get something over here, which will be at positive 3 now, because this was negative 3, so when I move 3 units to the right, I move 3 more, and I get positive 3, positive 2. And then if I flip it over the line y equals x, I'm going to draw this one a little bit bigger. So the line y equals x is all the points where y and x are the same. So 0, 0 is one of those points. 1, 1, so here's 1, 1. It's one of those points. 2, 2 is one of those points. The y value is 2, the x value is 2. Negative 1 is one of those points. Okay, so we end up getting this line here called y equals x, because y and x are the same. That's why it says y equals x. But we also have our point here, which was negative 3, positive 2. So if I'm going to flip that across this line, I need to make sure that distance is the same as when it goes on the other side. How do I do that? Okay, well, there's a couple ways we could do this. Now I'm going to tell you the easy thing to remember is that when you flip over y equals x, you end up just having the y becomes the x and the x becomes the y. So if this is negative 3 comma 2, we're actually going to end up at 2 negative 3. That's the shorthand way to remember it, and it's probably the smartest thing to do is just memorize that. When you go over y equals x, then these two just swap places. But if you want to know why they swap places, well, we can look at the equation y equals x. If I want to flip over it, I'm going to have to go perpendicular to it, which means I'm going to have to go across y equals negative x plus some b. And we don't know what that b is right now, but basically the only thing we really care about is the fact that it's a negative x slope, okay, which is going to help us whenever we try to make a right triangle to find out these distances. And all right, so that's how we're going to be moving it down there. But just to save time, guys, because I got a lot of this, you know what, I'm just going to quit right there. I'm just going to go ahead and tell you guys that we can go with memorizing 2 negative 3. Okay, so let's move on down. A figure is translated x comma y to x plus 7, y minus 1. What translation will move the image back to its original position? So basically this is saying take whatever your x value was and add 7 to it. Take whatever your y value was and subtract 1 from it. So if I do that, if I take a point and I add 7 to the x and I subtract 1 from the y and I get the new point, then how do I get back? Well, how do I get back to its original position? Well, I just walk that path backwards. I add 1 instead of subtracting 1 and to the y, and I subtract 7 to the x. So what I'm going to find is, to get back to the original point, walk that path backwards, and I'm going to have that x comma y becomes x minus 7, y plus 1. You'll notice that just basically switch the signs. But the reason why you switch the signs is because you're undoing what has been done to it. Undoing what has been done. Okay. I'm going to erase a little bit of this so it's not in the way. For the graph, I can believe they're talking about this graph on the right with the triangle in it. Draw the image of the given transformation. So 7e, a translation 2 units to the left and 3 units down. So we are here, and we want to go 2 units left and 3 units down. So we're going to go down 3 and we're going to go left 2. So if I start at this handsome point right here, moving over 2 units takes me there. But then moving down 3 units goes 1, 2, and 3. I'm going to end up right here. All right, so what if I just did that with all 3 of the points? I could do it physically and just look at it and say, hey, well, if I'm going to do that, then I can just go over 2, down 1, 2, 3, and then over 2, down 1, 2, 3. So it looks like I got 3 points here. I can pretty much draw in the triangle. See, Mr. Conaway, this is kind of messy. What if I just almost got it all? Look at that triangle separately. Go over 2, down 3, boom. Over 2, down 3, boom. And over 2, down 3, boom. And draw it in without all that mess. Now, they didn't put it in there, but might as well. We know it is a right triangle. The second one, so 7e is done. 7f, a rotation of 90 degrees clockwise about the origin. Now you might ask, what are they rotating? Are they rotating the original black triangle? Or are they rotating the second red triangle? Since they did not imply that this was compound, for the graph, draw the image of the given transformation. I am going to say that these are not compound and that we are going to do each of these transformations from the original shape in black. So now, rotation of 90 degrees clockwise about the origin. Now, if I had the ability to, I would show you that the easiest way to do this is to physically take the paper and rotate it 90 degrees clockwise. Now, what way is clockwise? Well, it's the way that a clock hand turns. This is clockwise. So if I want to go 90 degrees, that starts up here and turns to there. That is 90 degrees clockwise. All right. So if I do that, basically what I'm going to do is I'm going to take this whole thing and I'm going to turn it. So I'm going to end up turning this axis right here until it's right here. So really what I should do is kind of picture this triangle and where it is if I was to rotate that whole thing to the right. And I could see that, hey, you know what, this if this was really this, then this section here would be about right there. And let's see, this section here would be about right there. Oh, I think I went too far. And then finally I can throw in my third side. Did I draw that right? Maybe our grid's off a little bit. I don't think it's quite square. I think it's kind of rectangular maybe now that I've printed it. Okay, but is there a more algebraic way to do it? Yes, there is. If you do not want to do the visual method, and like I said, I normally would just do that by rotating my paper, but I can't do it electronically here. If you want to do the more algebraic method, you can remember that a rotation of 90 degrees clockwise is x comma y becomes, now two things are going to happen. One, they are going to swap variables. So the x is going to become the y, and the y is going to become the x. But two, one of them is going to become negative. So what was a positive 1 in the x is now going to become a negative y. Sorry, negative 1 in the y. So the x will become the regular y, and the y will become what the negative of the x was. So it'll be y negative x. That would be the other easy way to do that, and you could just go through and find all three of these points and say, look, this is the point 1 comma 2, so whenever I switch it around, the x will become the y, sorry, the x will be replaced by, I shouldn't say will be replaced by the y, so I should get 2, and then the y will get replaced by a negative x, 2 negative 1, oh, not 2 negative 2, 2 negative 1. All right, 7G, a reflection across the y-axis and a translation 2 units down. Now, we've done all of this on the same piece of paper, but that may be how the actual problem works, so we want to make sure we can do that. A reflection across the y-axis and a translation 2 units down. So this is going to be a twofold problem. Reflection across the y-axis, this is the y-axis. So I'm basically going to take this and reflect it in the mirror, and points over here, since it moves one space to the left, since this is one space, I'm going to move one space again. I'm going to here. And that's going to put this whole side right there. This side is 3 units long, so it's going to be 3 units long this way. And then, yeah, that looks like a reflection in a mirror. It sure does. I think we're doing right. Okay. So now that we've got a reflection in the mirror, the second part of it is let's translate that 2 units down. So I need to slide this thing 2 units down. So what was here is going to go 2 units this way, and it'll end up here, down, and across. This handsome striking feller here is our final transformation. Okay, 7H, a rotation of 90 degrees counterclockwise about the origin. Well, we're kind of running out of room here. I'm going to erase Greeny Weenie here because he's not necessary. He's not a final part. He was just a intermediary in the transformations. So if I do a rotation 90 degrees counterclockwise, that means the opposite of clockwise. So counterclockwise is going to start here and go backwards. And therefore, to do 90 degrees, I'm going to start at the top, and I'm going to end at the 1/4 mark here. So that means that this is actually going to become this after it rotates 90 degrees. And I'll just take that away. So a point here will rotate 90 degrees over into this area. And what we find is this is the coordinates 1, 4, and it's actually going to end up being -4, 1 right here. I would do that physically with my paper. I would turn it and record it, or I could come back here and once again know that there is a formula. And if you notice, it's very similar to this one. They just change. If you go negative 90 degrees, or counterclockwise 90 degrees, or 270 degrees clockwise, those are 3 of the same things, you're going to end up getting negative yx. So what was the y is replaced with the negative, sorry, what was the x is replaced with the negative version of y, and what was the y is replaced with the regular positive x. Okay, so that green dot represents that top point. This green dot's going to represent this point here. Instead of 1, 2, it's going to be negative 2, comma 1. And then instead of 4, 2, I'm going to get negative 2, comma 4. And that there devil is the answer to 7H. And I believe we've got all of our transformations out of the way on that graph. All right, number 7I. If ABC is going to be rotated around the origin, what are the resulting coordinates if 7I, it rotates 90 degrees clockwise? All right, so I guess the first thing we should probably do is get our original coordinates. So A looks like it has the coordinates of 1, comma 1. B has the coordinates of 1, comma 4. And C has the coordinates of 5, comma 1. Okay, if it rotates 90 degrees clockwise, we already wrote out the equation, so let's just rewrite it. XY becomes, and I believe this was the y comma negative x. I forget these things sometimes, guys. I mean, you know, you in life will go around and you'll look up formulas as you need them, but it is important to just know how to apply them. X comma y, this is a new one. If you rotate 180 degrees, what basically happens is things that were positive become negative, and so on and so forth. And it actually makes sense that if you do this twice, and I'll just erase this after I'm done, if you do xy becomes y negative x, then do it again, and you're going to have what was x is now y, but so I'm going to plug it in again. So plug y in for x, and then plug negative x in for y, and you're going to end up getting that the second time around, as this comes back around, you're going to end up getting that a negative x is supposed to be in place of what was the y, but sorry, it's going to be in place of what was the x, because x gets replaced with y, but our y is currently a negative x. So x is actually going to end up getting replaced with negative x. And then y gets replaced with what is the negative of x, but that is currently a y. So it's going to be a negative y. And that's how we get over to here. So basically what I just did is I did it once, twice, and 90 equals 180. So that's how we ended up getting to negative x, negative y, because we did this thing twice. And now I'm going to erase that horrible monstrosity of stuff I just wrote. If I can do it nicely enough. Boom. Look at that. All right, so now hopefully that made sense. If it didn't, just ignore it and move on. X comma y becomes negative y comma negative x. That actually would make a lot more sense if you used maybe an A and a B in place there. You would see it happen a little bit easier. That way you wouldn't get confused with all the, like I do, with all the X's and Y's and stuff. All right, so those are the three formulas. So let's just write what happens after you put them into three formulas. Pardon me. So A, B, C. If A is 1, 1, when I put it into this, well, I'm going to take the 1 from the y and put it in there. Okay, so that's 1. And the 1 from the x, and I'm going to put it in there, so that's going to be negative 1. Okay, so I'm going to do the same thing. The 4 is going to go in place of the x, because they swap. And the 1 is going to go in for the negative x, so that's going to be negative 1. I'm sorry, that might have been really quiet. I'm not keeping the mic up high enough. And then once again, 1 over here goes in place of the y. There you go. Because remember, the y is replacing the x. Okay, that's why I keep doing that. All right. And then finally, the 5 is going to go into the negative x slot, which means it's going to be negative 5. So there's our 3. Let's do the middle one. The middle one's easy. I'm just going to take an x and I'm going to put a negative in front of it, and a y and put a negative in front of it. So that's -1, -1. That's -1, -4. -5, -1. Love that one. And finally, so now, I'm sorry, guys. Y'all should have said something before this. Why didn't y'all say something to me and stop me? It's -y positive x. Thank y'all for catching me and letting me know about it. I know, I'm just hilarious. So xy becomes -y comma positive x. So plug in the 1 from here in place of the -y now. So that's going to be a -1 now. And then what was the x is going to stay positive. So it's -1 coming to 1. Okay, in the second one, what was the y? I'm going to throw a negative in front of it and put it in place of the x. There we go, -4. And then the same thing, I'm going to put the 1 in for x. Good. And so finally, -1 comma 5, I think, is the last one there. And there's all of your coordinates. By the way, guys, I can work these out. That doesn't mean that just watching it's going to let you do it on the test. So make sure that you're just using this as a tool to test yourself and to figure out what's wrong with your work. So you do need to go back and erase the answers or cover them up with a sticky note and retry them on your own so that you get a good chance to figure this out. So 7L, if the point t -2 -4 is translated through this translation, where is t, and I cannot see that. I hope it just says prime. Yeah, t prime. Okay, so after I take t -2 -4 and plug it in, then I'm going to say plug a -2 in here and a -4 in there. And I'm going to get that t prime is going to be -2 minus 3 and -4 plus 2. Or t prime is -5 comma -2. There we go. Tell what kind of symmetry each Greek letter has. Remember, a figure can have more than one type. So there's 3 types of symmetry that we can have. Arguable. Anyway, so we've got vertical, horizontal, and rotational. So if we look at each of these, let's see which symmetries we have. The epsilon here, you could cut it this way, and it is symmetric, so that makes it a horizontal symmetry. God, is this iota? Ah, shoot. Don't get me lying, guys. I'm ashamed to the profession. Okay, you got vertical symmetry here, and you got horizontal symmetry here. And generally, if you have both vertical and horizontal, I believe this is always, then you have 180 rotational symmetry, because it can be flipped on its across the x-axis and across the y-axis. That's the same as rotating it 180 degrees. So it does have all 3 symmetries. Okay, so X here, whatever letter that is. This is arguable. Fonts. I think I would ask my teacher, does the font size matter? Are they going to care? If I was grading this test, I would think that the concept is what matters more than anything, not the font. So if I just go off the fact that these are both legs and I'm not really worrying about, so let's just say this figure here, not really worrying about size, then yes, this has vertical symmetry, horizontal symmetry, and it has rotational symmetry of 180, but it also has rotational symmetry of 90 degrees. Okay, so this has 90 degree rotational symmetry, and 90 degree covers 180 because 90 twice is 180. So this has all 3. Now, if we were taking into context the thickness of the legs, the fact that this is a wide leg here, then it only has a 180 degree 180-degree rotational symmetry. Because you cannot flip it over this way because the fat leg would land on a skinny leg. And same thing here, you can't do it that way. So it only has 180 rotational symmetry. So that would be a question I would be asking your teacher. What do they mean? And finally, theta. All right. Oh, was that phi back here? I bet you that is phi. Phi. Wow. Can't believe I missed that. So, theta. Yes, we can cut it horizontally. Yes, we can cut it vertically. And 180 rotational. Okay, so it does have rotational symmetry of 180 degrees. Can't go 90 because if we went 90, then the little line would be facing up and down. It would look more like a phi than a theta. Okay. Man, one last and then we'll have a break for this one. What three regular polygons will tessellate? Okay, the key here is regular. Okay, the only way we can have regular is if it's equilateral and knock, knock, knock. This is going to be on the test probably. Equiangular equals regular. And for shorthand, all sides, all angles are the same. So in a, we got a triangle. We could have a three-sided triangle. We could have a four-sided square. We could have a, oh, this is going to embarrass me once more. Please no teachers watch me here. We could have a regular pentagon. We could have a regular hexagon. Mark, I know you're laughing, and I'm going to knock you upside the head next time I see you. Stop it. Okay. That's to the teacher, Mark, not the student, Mark. Let's see. Okay, so that's a regular hexagon. We could keep going, but you don't want to see me butcher anything else. 7 sides, 8 sides, 9 sides, 10 sides, blah, 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 blah. Only 3 of them will actually tessellate. Tessellate, as you know, means can I fill a pattern, a whole grid, with just that same shape? And check. Triangles work. Obviously, if you've walked across a checkerboard floor, squares work. And finally, though we would like pentagons too, and they do seem to make these nice little shapes on soccer balls, they actually are not going to tessellate in a flat plane. But honeycombs are made of hexagons. But hexagons are really just nothing but a bunch of these triangles anyways. So yes, hexagons work, but really it's kind of a fake, false, because they were already covered by triangles. So triangles, equilateral triangles, squares, and hexagons. And that is the end of page 7. I think we've taken way too much time for one recording. So I am going to, yeah, we're at 30 minutes. I am going to record on another show now for page 8.